Let's now take a look at the LIBOR market model or the BGM model. The BGM model is substantially more complex than the HGM model to analyze. So I'm gonna try to take it slow and also try to break it into smaller components so that we can understand it easier. Now, let's first take a look at how we can set up the model, and then we take a look at a concept called the rolling risk-neutral world. Okay, now to set up the model, we have a few notations. So let's use FKT to denote forward rate between time K to time K plus 1. So if you can imagine that on your entire curve, the term structure of forward rates, the actual forward rates, if you have a rate between rate between 10 points, the current point is 0, and then you have 10 points on another 10 points on the curve, then basically the T1 is really the forward rate. F1T is basically the rate forward rate between 0.1 to 0.2. So let's say each of them is 6 months, and you have 10 points on the curve. So basically you have 5 years worth of horizon out there. Then T1 is really the 6 month rate between 6 months to 1 year. That is 6 months out. Okay, and T2 is, no, actually F2T, T is always the current time. And K is then in relation to T. So F2T is, if T is currently, is the current time, then F2T is then the 6 months forward rate between 1 year and 1.5 years. So again, then F3T is then the 6 months rate from 1.5 year to year 2 to 2 years. It's a 6 month rate. So that's how we denote the forward rates. Just a convention here to help us analyze that. Obviously, you don't have to have K and K plus 1 being always a constant time period. So in the example, we talked about the 6 months. You don't have, maybe the first point is for a 6 month rate, the second one is for a 1 year rate, and third one is for a 1 year and 2 months. You don't have to have that, but typically, if you look at a real curve, you tend to have regular, you can actually, in a way, break them into regular intervals. So, but the model itself does not depend on you breaking them on the regular intervals. It just says whatever the FKT is really the rate between the rate between TK and TK plus 1, as seen right now at T. Okay, so if between TK and TK plus 1 is 6 months, then that rate is a 6 month rate. If between TK and TK plus 1 is 6 months, then it's a 6 month rate. Okay, it's always observed at time T. Okay, now the compounding period obviously is the difference between those two time periods. Now the second concept we need to talk about is this M function here. This is related to when we need to use the rolling risk-free rule. So this function is basically an index. So it takes the value of 1, 2, 3, 4, 5. It's an index that for the next reset date at time t. So right now, time t is some time index there. So it says is the smallest integer between t and t empty. So it takes this time as the a function and returns an integer value. We'll see in a graph in the next slide as an example, okay? So it gives you some sort of an index. And this thing here is basically just a volatility for this particular rate here. So for the k point k, that's the volatility term for the point k. And also this little t means the current time, okay, the time that the whole term structure is observed. So let's use a graph to basically show that. So first of all, what is MT? Now, these two lines are the evolution of time. It's the evolution of time if you can imagine that, it's like you can imagine the curve, the entire curve move from what you observe now to a future time point in the simulation. You can sort of try to imagine that, okay? So you start here. So your current time is here. So this is the first point. So from here to here is really the current interest rate. But from here to here is the forward rate between this period, okay? And tk equal to 1 time out. So if this is like a 6 month out for a 3 year, and if the period here is 3 months, then it's a 3 months rate, forward rate, 6 months out from right now. Now, if we are here, so it takes the function here, then the next reset time is 1. So the index of k is 1, 2, 3, 4. So because you are before the first index time on your entire curve, you are m is equal to 1. Now imagine that if you simulate the curve out, so if this is like a 3 months point, let's say you are like the 4th month. So let's say this is a 3 months out. Well, actually, let's say this is 6 months out in between the 3 months. So here will be like the 7th month. So if you use the next time point that you simulate is 7 months from today. So at that point, the curve you observe will not include this point. So at that point in time, the index, the original points you have on the curve, this one will drop out, and you still have this point, and this point, and so on, right? But at that point, this m would take the value of 2 in the simulation, okay? Because the second point is 6 months plus 3 months is 9 months. So this tk equal to 2 still exists. And this m is equal to 2 now. This basically means a second index, okay? So with that, what property does the forward rate, a specific forward rate that we observe right now, and we model its evolution in the future, what does that rate have, or that whole set of rates will have? Well, first of all, let's take a look at what is a forward rate, just to recall, how we derive the rates. A forward rate, under the definition we have provided, is basically a forward rate that we observe right now at the little t for a period between k and k plus 1. So we may have k being 6 months, k plus 1 means 9 months. So then it's a 3 months rate, 6 months out. Now that rate, how we derive that? Well, if we have a whole set of zero coupon bonds, that rate can be derived by using zero coupon bonds of current time to 6 months and current time to 9 months. And then divided by the price of zero coupon bond between current time and 9 months, right? So this will give us the forward rate 6 months out for 3 months. 6 months out for 3 months. Now, we see a ratio here. So if we see a ratio here, we can always create a martingale using, in this case, we can use this as a denominator. Then it's a numeraire here. So we use this zero coupon bond as a numeraire, and we call this difference another financial asset. Give a name, say F or something. And okay, so then this ratio of this difference divided by this will be a martingale. If this thing is used, which is the denominator here, is used as a numeraire. So we have df, the change of this forward rate, is this thing here, which just says it's a martingale, right? Now, this is only true when we use this thing as a numeraire. It's only true for this fk being a martingale. The process of fk is like this. So, but the fk plus 1 is not a martingale. Okay, so we cannot. So the reason is this is the because we're using this thing as numeraire, whereas fk plus 1 we have to use another zero coupon bond. So the zero coupon bond at the numerator is no longer this zero coupon bond. So the fk plus 1 is not a martingale if we continue to use this zero coupon bond as the numeraire. So when you look at the evolution of the entire forward rate curve, only one point along on the curve is a martingale, follows a martingale process based on a particular one that we selected, particular zero coupon bond we select as a numeraire. All the other ones will have a drift, okay? Now, for any specific k, if we make this k a specific k, then it means it's a point on that forward rate curve. But if you allow this k to be a variable, then this fkt means it's a collection of the forward rate, or it means the entire curve as observed at time t. So that fk, k being a variable, then is the term structure of forward rate. So here is just a review. You should actually go back and look at, what is a forward rate, and that we talked about earlier in lecture 3, and how a forward rate is related to the the martingale approach. We can have what is being used as a numeraire, and then this ratio, which is a forward rate, is a expected value of the realized one. So, and it's a martingale. So review example 3.4. That will help you understand the BGM model. Okay, let's move on to another concept which relies on this MT here that we need to understand. So it's called a rolling risk-free, the rolling risk-neutral world. By rolling, meaning that we actually change numeraire asset from time to time. So so we have to adjust the drift. Now we see that the forward rate can be expressed as a ratio of two variables, basically between this and this. So we can select a particular zero coupon bond as a numeraire, and in that we will have a particular world where that if that zero coupon bond is selected as a numeraire, then there's some probability measure there as well, and it's easier or very convenient to select the zero coupon bond that matures at the next reset date as a numeraire. So to basically analyze the evolution of the entire term structure of forward rates. And with the selection of that particular zero coupon bond, we basically have determined a probability measure that how the entire term structure of forward rate will follow. Okay, so we'll be evolving in a particular probability measure. Now, if we were to have a time t, this time t could be what we have right now, or as we evolve in the simulation, this t will take a different value. Then this t, which is always the next reset date. So if you evolve any points before you go across the reset date, this value doesn't change because m doesn't change. But if you go across the boundary of a reset date, then this m value will change, and this tm would be a different number. So we'll always use this p/t/tm as the discount factor and the numeraire. Okay, so if you look at on a chart there, initially p is the zero coupon bond between here to here is the numeraire, and then if the evolution occurs and the actual time that has moved to the current time has moved to this point in the evolution or in the simulation, then the zero coupon bond now used for the as a numeraire will be a zero coupon bond from here to here. Okay, so first one is from here to here. So if t comes from here, evolving here before moving this point, it's always a zero coupon bond from here to here initially, and then if t moves to here, then it will be from here to here. Okay, then it's closer from here to here. But if it's gone across, then this becomes 2, so that'll be from here to here. So like this, from here to here. So, and later on, when you move to here, then there's a zero coupon bond from here to here until they cross this reset time that you mark on the curve. Each point is for that particular forward rate that you are evolving, you are building a process for. So when the actual simulation time has gone across here, then this will become 3. So you're looking at a discount from here to here. Okay. So when the actual evolution time or simulation has that little t has moved across the reset time points, you then need to change the numeric asset. So because you are now using a different zero coupon bond as the numeraire, and then there is a change of the drift. Also that if you evolve the entire curve, as I mentioned earlier, only one point on the curve that follows a martingale process. All the other points are not following a martingale process. All the other one has a drift. The point that doesn't have a drift is the point of Fk. The process of Fk is a martingale if k plus 1, if m is equal to k plus 1, and the bond p from t to k plus 1 is used as the numeric asset, and then this particular point will then be will have no drift, will be a martingale. But let's say in that case, if a k1 is such a is such a point that follows a martingale process, k2, k3, k4, fk2, fk3, fk4, and so on, they all have a drift, but k1 would not have. But if the actual passage of time moves across the first reset point, then k2, because that point we still call it k2, then k2 will become the point where we'll have a zero drift, we'll have a martingale process, because now we have used a different numeric asset, so the evolution will be different. Then K3, K4, and K5, they will still have drift. They're different drifts, but they will have drift. But K2 will have zero drift because we have selected a numeric asset corresponding to that. That makes the process a martingale process. So what does the term structure of forward rays follow? Like what process does it follow? Well, mathematically, it will follow a process like this for any specified k and t. This process would have a, you will see it has a volatility term here. And it will also have a drift term that is written down here. Okay, now we'll explain why it takes this particular form. And recall that this V here is the volatility of the zero coupon bonds. So this thing is the volatility term for the forward rate, but here the V are the volatility term of the zero coupon bonds. So this V K plus 1 is really the zero coupon bond that between K plus 1 and T. And this one here is the zero coupon bond between M and T. So N depending on what number that M takes. So if M takes the value of K plus 1, then this term will drop out. So then K, for that particular K, there will be no drift here. So this part will drop out, and you only have this part, which is you will get a martingale process. So for example, if K equal to 3, and M is equal to 4, then K3T F3T will follow our martingale process. But if M is equal to 4, sorry, if F is equal to 2, for example, then F3T would not follow a martingale process because this term is not 0. Okay. So again, if K is equal to 3 and M is equal to 4, this will be okay. But if K is equal to 3, M is equal to 2, for example, that K F3T will not follow a martingale process. Okay, so here I've just basically drawn this thing here. So to tell us what this M is, to remind us what this M function is. So when actual evolution in the simulation moves to this point, then M will switch. You see that if the volatility term for zero coupon bond, let's say it's not a function of this little t, let's say it's just a parameter. This process for a period of time, this part will be a constant. Because if this is not a function of little time, and this thing here, unless the little t cross the reset time, this v for a period of time will be constant, even though your little t is moving forward in time. But once that little t move across a reset time, this m will take on a different value. Then this v will take on a different value. Then you have a jump here in the in the drift term here. So all of a sudden you have a jump. So in that process, in those processes where you make the volatility of the zero coupon bond just as a constant rather than a function of the little t. So you have constant for a little bit for a period of time, and then there's a jump. There's a sudden change, and then becomes constant for that. So it's like a step function. So it's okay for a period of time, then there's a change. It could be a positive change, it could be a negative change. Now, one of the questions people first time look at this will say, well, why there's only one martingale here? There's only one point on the curve is martingale, all the other one has a drift. And the other question people typically will have is, why is this thing? Why do we know this is the part on the drift and multiplied by this thing here? Well, first of all, we in a way have explained why there's only one point, because this is a particular value right? Because m takes a particular value, depending on for a period of for interval of t. If t is between a particular interval, this m is a constant value, and this v is a particular it's one of those vk's, right? It could be a vk plus one, or it's one of those ones. So there's only one of them that this one will cancel out. It must be the case where m equal to k plus one, and this one will cancel out. If m is not equal to k plus one, for all the other ones where you have this k being a different number, let's say if k is a 4, m is a 3, then this one is not 0. But if m is 3 and if k is 2, then this k, that particular point, will have a 0 drift. So therefore, there's only one point. Okay, we cannot have every single point, as we talked earlier. Now, why is this the drift term? Well, let's have a quick review of the equivalent martingale measures on change of numeraire. So if we were to change a numeraire from numeraire G to numeraire H, we have to change the drift. So you have a multi-factor model here for each of them, for each of the risk factor or the volatility, the factor that drives the random change, random factors there. There's this difference here between the risk price of H minus the risk price of G, okay? So it's related to this. Why? Well, if you are in the rolling risk neutral world, that means you are changing your numeraire from time to time. That's what the rolling means. The PTM is always the current numeraire, depending on what m value is. Okay, so now for any forward rate f k t, if the numeraire asset that will make this process a martingale is this v, it's a 0 coupon bond that is from k plus 1 to t, right? So we can call this new, if that is the numeraire asset, we can call that numeraire asset G. If that 0 coupon bond is the numeraire asset, then this process will be martingale. But unfortunately, that may not be the one that's been selected in the process. So the selected numeraire asset is dependent on this m here. So unless m equal to k plus 1, you have a different asset H being a numeraire asset. Okay, so you have to make a change of numeraire, and the change of numeraire, the adjustment is the difference between this two here, between the vol of the two different assets, between the volatility of parameter of the volatility function of the two numeraire asset, as we have seen earlier here. So therefore, you have to, this will give us the drift of the forward rate for a particular time point k here. So therefore, as I mentioned earlier, only one point along the forward rate curve follows the martingale process for a period of time. then all the other points they have a drift, and until then the switch is made, then another asset, another forward rate will follow a martingale process, and all the other ones would then also have a drift. Okay, so at any point in time along the entire curve, there's only one point that follows a martingale process with no drift. All the other points will have drifts.